Welcome back to another recorded lecture. Hopefully you're finding these helpful as you go through and review the different types of molecules that we're learning about in organic chemistry. So before we move on to this, just a quick recap. We've learned so far about basic hydrocarbons and the idea that each carbon is numbered in a molecule, and the name we give these structures helps give us information as to what is in what position. So if we start off with an example, before we move on to hear something such as for butyl 2-chloro non 3-ine. Sorry for sounding that out, just wanted to get it straightforward. So you've got a lot of information, and remember, every time you see a number followed by a dash, that's telling you the carbon that we're looking at and what is attached to it. So before we start drawing a molecule, we kind of scan from the right-hand side and we look for the first prefix from our original chart. And I don't get that until I see here, which is non. So non represents a 9-carbon chain. So what I can do here, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's a line diagram. It's a quick little sketch, and I can clean this up afterwards if I'd like. And now all I'm going to do is look for each number. You can see here I have 3 numbers, which means there's 3 portions to this molecule. So first off, whenever I draw them, we get to pick the numbering. So we're going to go from left to right, 1 to 9. Carbon 3 will have a triple bond, 1, 2, 3, right here. So this line diagram isn't accurate. After the triple bond, there should be linear bonds, and we'll redraw this after. But I've taken care of the triple bond. I've taken care of the parent chain. Carbon 2 has a chlorine group on it. We've taken care of that. And carbon 4 now has a butyl group based on this name. So 1, 2, 3, 4. Now, this structure cannot exist. All right, so it's a good little show as to why. Because if we look at this carbon here, right, it has 5 bonds on it. It's got 3 from the triple bond, 1 connecting to the next carbon, and then a side group. So if we think of a way we could change this, well, an easy one is just change the YNE to an E. We got rid of one of those double bonds. Now this structure works. The only thing we would have to add in is the cis or trans monomer. So if I look at this, I've got the hydrogen pointing down. So clearly this is the heavy chain on this part. Looking at these two, I've got a 1, 2, 3, 4 carbon chain here, 1, 2, 3, 4, 5 carbon chain here. So that one's heavier on the bottom. So really what I have is a double bond with its 4 substituents, and the heaviest 2 are on opposite sides, so I have the trans monomer. So to fix this, I would call it trans 4-butyl 2-chloro non 3-ene instead of ine. So that's just a quick little recap. When you see a big name like that, don't get scared about it. Just kind of put these little brackets underneath the number and what it's attached to, and that lets you start placing the components of the parent chain. So now we're going to get into things other than just carbon chains that are attached. We're going to get into functional groups. So functional groups, like you see here, change the properties of the molecule completely because we're adding in different atoms now. So we're jumping in terms of intermolecular forces, reactivity, lone pairs, all the different things that these atoms can bring. So in this lesson, we'll go through 3 different functional groups, alcohols, ethers, and thiols, and we'll see what they do. So our goal here is to be able to draw the 3 different types and describe the basic properties that affect their abilities as solvents. Now that means they dissolve other components. So there's many types of functional groups. In this lesson, we're going to focus on the alcohol-related ones, and they affect the naming of the molecule as well, because we have to get across through the name that there is that. You can see the different factors that are affected, right? So this should be a common theme by now. So let's go through and see how this is similar to what we've already learned. So an alcohol group is a compound that contains a hydroxyl. So this R just represents any carbon chain, and an alcohol group has an oxygen and a hydrogen bound to the chain at some point. Alcohols have higher boiling points than a similar length hydrocarbon due to the presence of hydrogen bonding. So you can see here if I draw the example CH3OH, which will look like this. It's methanol. So we're drawing hydrocarbons. Remember that the carbon is the parent chain. And then CH4. Very similar molecules. Both are going to be tetrahedral, but the presence of this group here introduces hydrogen bonding, which will affect its solubility and its melting point. So we already said it'll be higher in terms of melting and boiling points. And then in terms of solubility, because it's a polar molecule, now this should be soluble in water, whereas methane won't be because it's nonpolar with those insignificant dipoles. So we're always going to be connecting this back to our first unit on structures and seeing how we can apply those topics that we learned. So there's different types of alcohols, but in short, to name them, all we're going to do is look for the hydroxyl group, which is the OH, right? You can draw like that, or we can have it bonded in its Vesper shape just like this with the bent. And then when we look at the name of the molecule, instead of an E at the very end, it's going to end in OL with a number in front of it. So for example, we'll have something that says FN1-ol. We're going to scratch that. We're going to put propan-1-ol. Okay. Just to give you a comparison, propane, if we were to draw that, would be a 3-carbon chain with all hydrogens around it. But because we have the 1-ol, that means on carbon 1, there's an OH group, and that's it. So the rest of the molecules are going to be filled in, or the rest of the atoms will be saturated by hydrogens. As a line diagram, start with a point, 1, 2, 3. So propane looks like a little upside down triangle, and then we'll continue the zigzag pattern with the OH. You can see I wrote the OH backwards. It's important that the oxygen connects to the carbon, less so that it says OH, more so that the right atoms are bonded together. And if this was propane, we just wouldn't have the OH there. So that hopefully gives you a visual as to what it looks like. So this is just a classification. It affects the properties, but not how you would go about naming it. So primary alcohol, the hydroxyl group is attached to a carbon that is only attached to one other carbon, which we're missing from here. So we'll just add that in. So you can see the example is buten-1-ol. We're going to use that naming system. The first one exists, but it's limited. So we'll focus on the one I showed you on the previous slide. So here, this bond here, and if you'd like to see the electron pairs, this carbon that the hydroxide is connected to only has one other carbon link. So that's considered a primary alcohol. These pack well and are very generally reactive. So these tend to have higher melting points than the types that we're about to see. And we'll summarize that at the end. Secondary alcohols, if you haven't guessed the pattern, it just means that the oxygen and the carbon that it's connected to is connected to two other carbons itself. Okay, so sometimes you'll see this symbol here, secondary, with a 2 with a little degree sign beside it. All right, so you're starting to see more branching here. You're getting something called a bulkier molecule that has real implications on its properties. We're trying not to use this style of naming, so if you want to guess and pause, how would you rewrite that? And if you did, you should have written with the number right in between there. So buten-2-ol. And I know some of you are going to be wondering, well, what if there's a double bond? The exact same thing we've talked about, we would just change that to En or Yn if it was a triple bond. So it still follows all of our rules, we're just making the name more informative. Lastly, you have a tertiary alcohol. You can see this is a really bulky molecule, and you've got the OH group connected to the carbon that's connected to 3 other carbons. So if you can, try to understand why there would be no quaternary alcohol, which would be a carbon with an oxygen connected to 4 other carbons, something like this. Can you imagine that? And if you thought, well, carbon can only have 4 bonds, you're correct. So that can't exist. It can only have a maximum of 4 bonds on a carbon molecule under these conditions. So to compare these 3 side by side, you can see that these are very linear and easy to pack. These are bulky, and the implications of that are up here listed. The bulkier it is, the weaker, the intermolecular forces become because there's less surface area to interact with. It would be like putting two soccer balls against each other, very low surfaces touching, versus if you lie two sheets of paper, which are linear, you would have an entire surface in contact. So with the primary alcohols, they have higher melting and boiling points, and they are more soluble. Okay, so this affects patterns that we've talked about. Polyalcohols are a type of alcohol where there's more than one OH group. Again, if you've seen this in biology as part of your um, big molecules in biochemistry, it's the glycerol molecule. It's the precursor to the fatty acid. So all we use is the prefixes and the numbers like we have been. The diol would tell us that there are two hydroxyl groups, triol for three, and the numbering with commas in between. So in this name here, just want to apologize, that E should not be there because we've dropped it for the OL ending, which indicates an alcohol. Okay, and a quick little biology connection. This is just for fun, right? When we combine this with the fatty acid chains, what we're going to get is that dehydration reaction, and this is coming later on for us, and that's how we build these molecules. So you can hopefully start to see the link between those. So when we're naming alcohols, same thing, start with the parent chain, make sure you know what that prefix is, and build it from there in pieces. Now we're numbering so that the alcohol has the lowest number possible. So we talked about this idea of priority, right? So far we said that we'll start from low and we'll move down to high. Okay, the lowest was the single bond. Then we moved up to a double bond, then triple, and now we're at an alcohol. So whichever, if they're all present, you always start with the highest priority. This gets the lowest numbering when you're naming things. So you start on the side that's closest to the alcohol. If the alcohol is not there, you would start closest to the double bond, etc. And that chart on the earlier slide gave you the overall order of polarity of all of the functional groups, and it's really based on reactivity. So aromatics that are named with the hydroxyl group on them will use hydroxyl as a substituent. For example, if we have something like this, or where the alcohol is not the priority, right? If we just have that, let's say we've got a benzene like that. The parent chain here is benzene because there's no longer a ring. So we can say that, but it's not going to be benzenol. We learned back in our aromatics lesson, there's quite a few names or different types of versions of benzene. So here, if we label this as number 1, it's got the highest priority. Then number 2, a halide would be just above a single bond, so we could fit that in here. And those are chlorines, fluorines, etc. Right, so in this case, alphabetical order, and I like to build the names off to the side. So we've got 1 hydroxyl, 2 chloro. Okay, even though the hydroxyl has a lower number, we put them in alphabetical order. So we've got 2 chloro, 1 hydroxyl, benzene. Okay, so anytime, excuse me, the OH group is not priority, it's named as hydroxyl rather than OL. So in this example, we've got pentin 2-ol. So let's break down the name. Pent is the parent chain. It's a 5-carbon chain. AN tells us that it's an alkane, which means carbon-carbon single bonds. And this means on carbon 2, there is an alcohol group. So if we look at the drawing here, off to the right-hand side, clearly this side has to be number 1 for that carbon to be 2, 3, 4, and 5. So to draw this from the beginning, I could start with a line diagram, and then on carbon 2, from left to right, I would put the OH group. These two molecules are the same, they're just mirror images. If I flipped the molecule that was drawn originally, I'd end up with the first one. It's identical. All of the atoms are in the same place, so both of these are okay to draw. Generally, we draw from left to right. So let's try this next one yet. And again, we want to get rid of that E because we have the OL. So the parent chain here is prop. That's a 3-carbon chain. So let's start with that. And we can always redraw it if we draw the wrong cis or trans isomer. On Oh, we've just made a mess of this name. We're going to fix this after. So the 1 should be between propene. That tells me on carbon 1, there's a double bond going to carbon 2. It also tells me on carbon 1 and 2, there's an hydroxyl group because of the OL ending. So this is an alcohol. So I've got an OH on carbon 2 and an OH on carbon 1. Okay, and if you're wondering, well, why did you put the OH group up instead of down? Well, now I have to check if I did that right. So remember, even though we're not showing it here, there is a hydrogen sticking off of this carbon. Okay, but we avoid that on the line diagram. So if I splice this in half, OH is heavier than hydrogen, and OH is heavier than one carbon. So both of the heaviest groups are on the same side of the molecule. That is the cis isomer. If I wanted to draw the trans isomer, starting with the double bond, I would have to have the OH groups in this case on opposite sides of this kind of horizontal plane that the double bond run throughs. So that would be the trans isomer of this, and we'll talk about packing later on, but because of this bulky C pattern, this this is considered bulky. So this won't pack as well. This is more linear. This will pack very well. So if you think which one of these isomers, even though they're the same molecule, have a higher boiling point, it'll be the trans isomer in this case because they can pack more together and their intermolecular forces can interact. So before we go on to that, this ends the alcohol functional group. There's not much more to it other than what it is, what atoms make up the functional group, and seeing how it affects the overall name of the molecule that we're drawing. So a variation of that is the thiol. So in group 16 on the periodic table, you've got oxygen and sulfur. So it's going to be very similar. Instead of OL, we will use THIOL as the ending. These are smelly compounds. These are kind of like that rotten egg smell, so you're probably familiar with them without knowing it. So in the example here, this E was just rampant throughout this presentation. Apologies. In this case, we've got a 3-carbon chain here, 1, 2, 3. Again, this is not a carbon because it's pointing to an atom. So you've got the thiol group. You can imagine it's got its 2 lone pairs above there. And we just replace the E of propane with thiol and the position of the carbon it's on. If I did the same molecule, but put the SH there, that would be propan 2-thiol. Okay, and this is a very important functional group in biochemistry. It leads to the disulfide bridge, which is a very strong connection in protein folding, and it's essential for all of our proteins to develop that strength to withstand denaturing. There is no propane 3-ol in this case because if it was here, then we would just number the chain 1 from that side. So in this case, we can only have 1 or 2. But if there were more functional groups, then we could use the 3. Right. So that was short, very similar, all the same properties as an alcohol, but with a sulfur instead. Ethers are a bit of a different compound. So an ether is an organic molecule that has an oxygen between 2 carbon chains, right? In terms of reactions, again, if you've studied biology, we condense 2 alcohols together to remove water, and that forms this functional group. Why is it bent? Well, because oxygen has 2 lone pairs on it, so that would make it AX2E2, which is our bent shape. And I'm always trying to relate it back to our first unit where we studied the structure and the intermolecular forces because these are the applications of it. So now if we look at this, there is no hydrogen bonding in this case. There's no hydrogen present on the oxygen. So it'll have an intermediate boiling point between an alkane and an alcohol if the carbon chains are similar. This is key. The carbons have to be the same or similar. The uses of ethers, because they are polar and nonpolar, they have the dipole here. We did the electronegativity difference for carbon and oxygen, right? It will have a dipole. But they can also dissolve nonpolar solvents because you've got these carbon chains sitting off to the side. So very, very useful in a lot of different settings, mainly industry. So to name an ether, there's 2 methods to add, as if there wasn't enough to know, but we're still adding this in. Number one, add oxy to the end of the smaller hydrogen or the smaller hydrocarbon. This is more universal. So for example, methoxyethane. So ethane will be the parent chain. I can draw a 2-carbon chain here. Methoxy tells me that there's a methoxy group, which is a oxygen carbon with 3 hydrogens bound to it. So this is actually its own group here. This bonds to the other chain, and we're left with this molecule here. We'll draw the structural diagram just to go back to our roots. Practice showing all of the hydrogens. And again, I drew it bent because that's what it should be. If there was more than 2 hydrocarbons here, you would have a number in front telling us which carbon the methoxy goes on. The other method of naming is to treat both of these as side groups and end the molecule in ether. So if we look at this here, methyl propyl ether. So it's an ether. Oxygen is going to be in the middle. One side has to have a methyl group on it. The other side has a propyl group, which is a 3-carbon chain. So 1, 2, 3. So that's what that one looks like. I'd like you to pause here and try to draw this one. And if you're just coming back from trying, you see that it ends in ether, so we'll start with an oxygen. There's a methyl on one side and a methyl on the other. Okay, so very same. And then to confuse it even more, we can just shorten that to dimethyl ether. Any of these are acceptable, so just pick one of the naming systems and stay consistent. This one here is the one I would have to recommend because it's more universal when there's more functional groups present. So that ends that to the lesson of functional groups, the introduction to it. Again, they follow all the same rules. It's just a hydrocarbon chain that's had a modifier attached to it and the ending change. So if I can give you one example before we go from here, I'd like to draw. I'm going to start with a cyclic compound this time. Throw a chlorine on there. Throw that group on there, and we'll start with that. So in this case, we have our main hydrocarbon is a ring structure. So I can list my points off to the side. It should have cyclo in the name. It's a 6-ring carbon chain, so the prefix in this case will be hex. We look around, we only see single bonds, so that makes this easy. We're going to say that the ending should be A-N-E. We're going to number these again. The oxygen gets priority, so that's number 1, that's number 3. So carbon 3 has a chlorine group on it. Carbon 1 has a methoxy group on it. Just fix up that name here. Methoxy. So a group attached to the oxygen is the oxy side chain. So when we put this all together, I'm going to start with it in alphabetical order. 3 chloro 1 methoxy. And then we go right into cyclo. There's no number, so no dash. Cyclohexane. If there was a double bond somewhere, if we wanted a variation, this would change here. Okay, so hopefully that helps. When you're naming the ether group as a side chain, just put the name of the carbon length chain and oxy as the ending to see it attached. Try to get into the habit of drawing the electron pairs as we know what the effect of those are. So hopefully this helps. Be sure to really go back and watch the examples again and ask if there's anything you get stuck on with the finer details.